Generally, in valence bond theory, I told bond strength depends on nature of the overlapping, nature of the shells, and nature of the overlapping, nature of the subshells, nature of the shells, nature of the overlapping. Okay, so some bonds are strong, some bonds are weak in one particular molecule. Overlappings are different. In case of hybridization, what it the central atom makes all the orbitals all the bonds equally strong. Central atom makes all the bonds equally strong by redistributing their energies. So we'll discuss how it happens. Hybridization. First, I'll give the definition. Process of intermixing of right now. Process of intermixing of atomic orbitals of process of intermixing of atomic orbitals of atomic orbitals of nearly same energy. Nearly same energy. It should be intermixed. First condition is intermixing. Second condition is atomic orbitals must have nearly same energy. Energy difference shouldn't be more. To form hybrid orbitals of to form hybrid orbitals of one a small correction you do to form equivalent number of hybrid orbitals of same energy. Hybrid orbitals of same energy. Hybrid orbitals of same energy. Whatever the orbitals undergoing hybridization, they must have nearly same energy, and we get equivalent number of hybrid orbitals of same energy and shape. Same energy and shape. Same energy and shape. Process of intermixing of atomic orbitals of nearly same energy to form equivalent number of hybrid orbitals of same energy and shape. Nearly same energy atomic orbitals are undergoing hybridization. Afterwards, the hybrid orbitals produced they are having same energy and shape, identical energy and shape. So this nature of overlapping also depends on shape of the orbital. In hybridization, all the orbitals get same shape. Energy also same. So central molecule is making all the bonds are equally strong by redistributing their energies. Here I'll give one general example just for understanding purpose only. A father has 3 sons. In that 2 well settled, third one is not settled properly. Father may not be so happy by seeing the first 2 kids. Will be very happy, but this third one, he is not settled. No, some way he get that feeling he should be settled like that. So that time he try in all the directions to make him proper. Who is not proper? Third one is not proper. I said not settled. No, try to. In that moment he can arrange some funds from his remaining sons, or he may help different ways. Okay, he somehow he try to make the third one also. Then only he will be stable. He will be happy. In the case of human beings, happiness will say. Here stability will say. So that time father will be happy if three members are in equal position. In hybridization, main intention is to make all the bonds are equally strong. Okay. So how it makes all the bonds equally strong, we see. So here, first of all, what are the conditions of hybridization or features of hybridization? Yes. Hybridization. So I told you only central atom undergo hybridization. Only central atom undergo hybridization in that valence shell atomic orbitals. Orbitals present in valence shell undergo hybridization. Undergo hybridization. So in complex compounds, sometimes inner orbitals will involve that we will learn in second year. Generally, valence shell orbitals undergo hybridization. Next one, even lone pair of electrons involved in hybridization. Means we have to consider lone pair of electrons also. If central atom has lone pair of electrons, lone pair of electrons also we have to consider hybridization. Next, pi electrons are not considered in hybridization. Pi electrons will not participate in hybridization. Pi electrons. Next, so by knowing the number of sigma electrons and lone pairs, we can decide the hybridization. We can decide the hybridization. Decide the hybridization. If this sum is equal to 2, SP hybridization students. If this sum is equal to 3, SP2. If it is equal to 4, SP3. Means number of sigma electrons and lone pairs. Lone pairs. If it is equal to 2, SP. If it is equal to 3, SP2. 4, SP3. 5, SP3D. 6, SP3D2. 7, SP3D3. See students, 1 plus 1, 2. 1 plus 2, 3. 1 plus 3, 4. Like this, sum should be equal to this number. 2 SP hybridization, 3 SP2, 4 SP3, 5 SP3D. Next one. Types of hybridization. Types of hybridization. Just now I told you no SP, SP2 hybrid. First one is sp hybridization. sp hybridization. In this, one s orbital, atomic orbital, and one p atomic orbital will undergo intermixing. Form. So here two atomic orbitals are intermixing. Students, listen first. Later you can copy. Students, can you hear me?
Yes.
One s orbital, one p orbital. Total two orbitals are involving. Two orbitals are means intermixing, involving in intermixing. I told in the definition forms equivalent number of hybrid orbitals. Equivalent number of hybrid orbitals. So here 1 plus 1, two atomic orbitals are involved. Two hybrid orbitals will get two sp hybrid orbitals. 1 plus 1, 2. Two sp hybrid orbitals will get. Next one, hybrid orbital is represented with, you represent it like this. One is small lobe, another one is big lobe. Small and big. You are not supposed to draw like this. If you do like this, it is a p orbital, dumbbell shape. So you don't write like this. So this is hybrid orbital representation. Any hybrid orbital is like this one. Hybrid orbital. Look at this, students. Now this sp hybrid, two hybrid orbitals are there. No, this is one hybrid orbital. This is one hybrid orbitals. Two hybrid orbitals are there. No? If two hybrid orbitals forms, they arranged in linear manner. So whatever the molecule undergo sp hybridization, its geometry is linear. If geometry is linear, bond angle how much, students? (180 degrees). 180 degrees. Example for the molecules undergoing sp hybridization. BeCl2, CO2, ethine, you might be knowing C2H2, triple bonded compounds undergo sp hybridization. Ethine, C2. One molecule I'll take and I'll explain how it is undergoing sp hybridization. Students understood sp in sp hybridization, one s orbital, one p orbital. S orbital shape is spherical, p orbital shape is dumbbell. But after hybridization, s orbital lose its shape, p orbital lose its shape, and they convert it to one identical shape. So if they are having identical shapes and identical energy, overlappings of all the hybrid orbitals will be same. If overlapping is same, strength of the bond also same. In that way, central atom makes all the orbitals equally, all the bonds equally strong. Now, in beryllium chloride, beryllium how it undergo sp hybridization. First, central atom in this, I told only central atom undergo hybridization. So beryllium atomic number 4, yes, central atom is beryllium atomic number 4. Electronic configuration is 1s2, 2s2. Electronic configuration of beryllium is 1s2, 2s2. And I also told one more point, valence shell orbitals undergo hybridization. So here valence shell is second shell, 2s I am taking. Second shell is the valence shell, students. So here 2p orbital will be there. First shell contains only one subshell, that is 1s. Second shell contains two subshells, those are 2s, 2p. So p subshell starts from second shell, d subshell starts from third shell, like this. Now s is having one orbital, p subshell has three orbitals. So according to the electronic configuration, 2s contains two electrons. So I am arranging like this. P has no electrons. So as it is electronic configuration, if you write in orbital form, it's called ground state electronic configuration. You are not changing anything. As it is, you are writing without changing their energy. Writing. In 2s, two electrons are there. The 2s two electrons we arranged in 2s orbital. 2p no electrons. Now here, if you understand, be easy. Beryllium is combining with how many chlorine, students? Beryllium is combining with two chlorine, means it has to form two bonds. For that, two hybrid orbitals it has to create. Two hybrid orbitals it has to create. Now, electrons are present in only s. And for the overlapping, it needs unpaired electron orbital, not paired electron orbital, isn't it? Orbitals which are having unpaired electrons undergo overlapping. So what we have to take, we have to unpair this pair. Unpair this pair. Easily it won't happen. So you have to give energy. If you give energy, this electron will be promoted to 2p. That is the reason. Slightly different in energies. In definition I mentioned. Slightly different in energies. If the energy difference is very high, electron cannot promote. So if you give energy and unpair the electrons, no, that is called excited state. Higher energy state. Excited state means higher energy state. So here one electron will be promoted to 2p orbital. Now from 2s we got one unpaired orbital. From 2p also we got one unpaired orbital. So now to get two unpaired orbitals, sorry. So now just S and P will intermix. So which hybridization, students, it is? SP hybridization. In this way you can decide. SP hybrid. One not two or three examples. Not only even 2, 3 are not required. Next example, if I do, you can understand it better. So based on the number of bonds create number of unpaired electrons. Clear, students? Here beryllium is combining with two chlorine, so we need two unpaired electrons. Two unpaired electrons. So sp hybridization, I said no, it is linear. Linear. So beryllium created, this is one hybrid orbital, this is one hybrid orbital. Here one electron is there, here one electron is there. This is about beryllium. This unpaired electron orbital of beryllium will overlap with the p orbital of chlorine. Like this. Like this. Now, central atom is beryllium. These are the chlorines. First, it makes the two orbitals equally strong, then it undergo overlapping. BeCl2. See, students, sp hybrid orbital of beryllium is overlapping with p orbital of chlorine because the last electron is present in p orbital only, no, in chlorine. 2s2 2p5. Last electron is 3s2 3p5, not 2s2. 3s2 3p5. Last electron is present in p orbital. Next, here also same thing. sp. And all hybrid orbitals form sigma bonds only. One more important point. All the hybrid orbitals form sigma bond only. So through sp and p orbital overlapping, we are getting sigma bond, sigma sp p overlapping. The nature of overlapping between beryllium and chlorine is sigma sp and p. Got it, students? Next one, sp2 hybridization. Okay, students. Next one, sp2 hybridization. You only tell students which and all orbitals undergo overlapping or intermixing and how many. In sp2 hybridization, which orbitals undergo intermixing? One s orbital, two p orbitals. sp2, right? sp2. One s orbital, two p orbitals intermix to form. How many hybrid orbitals, students? How many hybrid orbitals will form?
3.
Very good. Sandra, correct answer. Correct answer. 3. sp2 hybrid orbitals. If two hybrid orbitals form, they arranged in linear manner, isn't it? If two hybrid orbitals form, they arranged in linear manner. If three hybrid orbitals arrange, they arranged in triangular planar form. Triangular planar form. One is like this, one is like this, one is like this. Triangular planar form. So this is one hybrid orbital, sp2 hybrid orbital. This is one. What is the shape, students? Triangular planar. Planar. If it is triangular planar, what is the bond angle? No, 120. 120 degrees. This is also called triangular planar hybridization. Srivani, correct answer. Now, example for sp2 hybridized molecules. BCl3, SO2, SO3, and ethene, C2H4, etc. Now, I'll take BCl3 and I'll explain. Here also central atom is boron. Its atomic number is 5. Its atomic number is 5. Electronic configuration is 1s2, 2s2, 2p, 2p1. So here valence shell is 2s, second shell. Second shell is the valence shell. So there are 2 electrons in 2s subshell. 1 electron is in 2p subshell. Right, students? S subshell has only 1 orbital. P subshell has 3 orbitals. In S there are 2 electrons. In P there is only 1 electron. So if you write as it is in orbital form, it is called ground state electronic configuration. Now you only answer my question. Answer my question. How many unpaired electrons we need, students? Here, BCl3.
3.
Arman, correct answer. Sandra, correct answer. 3 unpaired electrons we need. Why 3 unpaired electrons? Because boron is forming 3 bonds, isn't it? Yes, Srivani, correct answer. For 3 bonds, 3 unpaired electrons we need. Okay. So, what to do? Go to excited state. You just supply some energy. Then this pair will be unpaired and will go to 2p. 2p. Now, 3 orbitals are having unpaired electrons. 3 orbitals are having unpaired electrons. 3 unpaired electrons are ready. In that, 1 is from S, 2 from P. So, which hybridization, students? sp2. sp2. Easy it is. sp2 hybridization. So, the 3 hybrid orbitals will be arranged like this. So, based on the nature of hybridization, is the hybrid orbitals oriented in particular geometry. If 3 are there in this way only, in order to minimize the repulsions, see students, here one unpaired electron, here one unpaired electron, here one unpaired electron. Here, these hybrid orbital of boron will come by overlapping with the chlorine orbital form like this. This is chlorines, this is chlorines, this is chlorine. This entire thing belongs to boron. This way, BCl3 molecule will form. So here, which type of overlapping, students? Sigma sp2p. Here also same thing. Sigma sp2 d orbital. So what and all things you have to keep in mind while finding hybridization? First, you have to write electronic configuration as this. Afterwards, ground state by taking only valence shell. Afterwards, you have to check central atom form. How many bonds are surrounded by central atom? So many unpaired electrons you create. So many unpaired electrons you create. And which and all orbitals are involving. Based on that, give you the type of hybridization. Got it, students? sp3 hybridization. Next one. sp3 hybridization. One s orbital and 3 p orbitals form how many sp3 hybrid orbital students? 4. 4 sp3 hybrid orbitals. 4 sp3 hybrid orbitals. These 4 sp3 hybrid orbitals are oriented in tetrahedral manner. So, finding difficult to draw this thing. Tetrahedral students, you make it little proper. 4 hybrid orbitals arranged in tetrahedral. So bond angle is 109 degrees 28 minutes. 109 degrees 28 minutes. Here example for sp3 hybridized molecules CH4, NH3, H2O, CCl4, NH4 plus undergo sp3 hybridization. Undergo sp3 hybridization. Here also we'll take one or two molecules to explain the hybridization. How they undergo sp3 hybridization. Afterwards, I'll give one shortcut method how to find out hybridization for competitive examinations and all. Without doing all these things, how to find out hybridization of various molecules directly. This is theoretical process, students. After explaining theoretical process, I will explain shortcut. Here, CH4. You only tell me, students, CH4. Which atom is undergoing hybridization? In CH4,
Carbon.
carbon is undergoing hybridization. Atomic number 6. 1s2, 2s2, 2p2. So ground state electronic configuration, can you tell? In 2s there are 2 electrons. In 2p there are 2 electrons. We arranged in different orbitals. How many unpaired electrons we want? How many unpaired electrons? 4. Yes, 4. Because carbon is forming 4 bonds. So what to do? We have to unpair the 2s electron. That is called excited state. These times now 4 orbitals generated. Each orbital is having one electron. So from 2s 1 orbital, from 2p there are 3 orbitals. So hybridization is sp3. Hope you understood at least now. This case sp3 hybridization. sp3 hybridization. Undergoing sp3. Next, NH3. One more condition I'm going to cover by taking NH3. I told even lone pair of electrons undergo hybridization, right? For that one example I am taking, including lone pairs. NH3 also you put side heading, students. NH3. Here central atom is nitrogen. Its atomic number 7. Electronic configuration 1s2, 2s2, 2p3. So the valence shell is second shell, contain 2 electrons in 2s orbital, and in 2p contains 3 electrons in 3 orbitals. How many unpaired electrons we need? Here 3 unpaired electrons. That's my correct answer. 3 unpaired electrons we need. Already 3 we have. So no need to go for excited state. We have 3 unpaired electrons. Required number of unpaired electrons 3. We have same. So no need to go for excited state. And then how to decide hybridization? This one also you have to consider. Lone pair also you have to consider. sp3, because it is also going to affect the geometry of molecule. So lone pair of electron also affect the geometry of molecule. So we are considering shape of the molecule. It will affect the shape of the molecule. We have to consider this one. So sp3 hybridization. In the features I told, lone pair also we have to consider. Hybridization. So these 3 electrons will form 3 sigma bonds and 1 lone pair. 3 plus 1, 4. I told no, 3 plus 1. 4 means sp3 hybridization. 2 means sp hybridization. Got it, students? Now, sp3d. sp3d. You only tell students which and all orbitals involved in this hybridization. You can unmute and tell instead of typing.
1s plus 3p and 1d.
Very good. 1s and 3p orbitals and 1d orbitals intermix form how many hybrid orbitals? 5. And my correct answer. 5 sp3d hybrid orbitals. This sp3 hybrid orbitals geometry is, this is trigonal. If I draw one bond like this, one pyramid, here one pyramid. So this total shape of this molecule is, geometry of this molecule is trigonal bipyramidal. Trigonal bipyramidal. Molecules which are undergoing sp3 hybridization, they have the geometry trigonal bipyramidal. Trigonal bipyramidal. 5 hybrid orbitals arranged in trigonal bipyramidal manner. 5 bonds. Trigonal bipyramidal. Here, 2 types of bond angles are there, isn't it, students? 2 types of bond angles are there. In trigonal planar, what is the bond angle? 120. Here, if you observe 90 degrees, you can see 90 degrees here. 90 degrees. Just it is a triangular planar above this. Above this. Planar 90 degrees. So the bond angles sp3 hybridized molecules are 90 degrees and 120. In triangular planar, bond angle is 120. So those above bonds are there, no? Those are called axial bonds. Those bonds are called axial bond. This bond and this bond is called axial bond. These bonds are called equatorial bonds. Equatorial bond. Equatorial. Example for sp3 dehybridized molecules PCl5 I3 minus XEF2 etc. These are the important examples of sp3 dehybridized. We will see, we'll find out hybridization of PCl5. What is the central atom, students, here? BS2 PP3. Valence shell is third shell. GS2 3p3. How many unpaired electrons we want?
5.
5.
5 unpaired electrons. So for that, here 3D will be there. Third shell contains 3D also, students. 1, 2, 3, 4, 5. Third shell onwards, 3D also starts. 3D subshell. Now, first excited state I am writing. First excited state. What will happen, students? This electron will promote to D. So, one electron. These 3 electrons will remain as these. This third, this unpaired electron will go to D. So, from S, 1 orbital, from P, 3 orbitals, from D, 1 orbital. Total which hybridization it is? sp3d hybridization. sp3d2. sp3d2, you only tell which and all orbitals involves. Tell me, students. Which and all orbitals involved in hybridization? What? How many?
1 is 3p and 2d.
One is 3p and 2d orbitals. Here itself you can write here 3. 1, 3, 2. Only so much. Yes, how many hybrid orbitals, students? Aishwarya,
6.
correct answer. 6 sp3 d2 hybrid orbitals will get. These 6 sp3d hybrid orbitals arranged in this is square planar. Above one bond, below one bond, if we draw, it is called octahedral geometry. Octahedral geometry. 6 bonds, 6 hybrid orbitals arranged in octahedral manner. So a molecule gets octahedral geometry. Octahedral geometry. Example for octahedral geometry molecule, hybridized molecule, SF6, sp3d2, SF6, XCF6, we see XCOF4. Yes. XCF4 also. These are all undergoing sp3d2 hybridization. And I will tell you how they undergo. All the molecules I will explain you, don't worry. Theoretically, I will take only few, but I told you, shortcut method is there. Bond angle here, one is 90 degrees. Students, suppose this is plane. You can consider this is triangular plane or square planar. It's not a square planar. You just consider it is square planar. Above one bond is there. Below one bond is there. Below one bond will be there. So this bond and this bond will be there. No, these two makes bond angle 90. Bond angle 90. And in between here in square planar it makes 45 degrees. Here also two types of bond angles. Example. Now SF6 I'll explain how it undergoes sp3d2 hybridization. SF6 central atom is sulfur. Its atomic number 16. Electronic configuration 1s2, 2s2, 2p6, 3s2, 3p4. Ground state electronic configuration. So here 3s has 2 unpaired electrons. 3p has 4 electrons. 3s has 2 electrons. 3p has 4 electrons. 1 electron, here 1 electron, here 1 electron, here pairing takes place. How many unpaired electrons we need, students, here? How many
6.
unpaired electrons?
6.
How many?
6.
6.
6 we need because sulfur is forming 6 bonds with the 6 chlorines. So here in ground state, how many unpaired electrons we got? Only 2. So first excited state, 3D will be there now here, right as it is. So this will be promoted to JD. Now how many unpaired electrons we got, students? Check once. 1, 2, 3, 4 we got. 4 unpaired electrons we got. So these 4 unpaired electrons is not sufficient. So we have to unpair one more. So if you unpair second pair, it is called second excited state. So far, with first one excited state only, we got sufficient number of unpaired electrons. Here we are not getting. So second time you have to give energy. That time this pair will be unpaired. So what is the hybridization, students? sp3d2. Nothing is there. Easy it is. Properly, if you understand, no, lot of time you can save in next year. And important chapter also. One question is compulsory. Minimum one question is compulsory for NEET examination, JEE exam. NEET examination sometimes two also they are asking two questions. In JEE once 1 year, two questions, three questions they asked from chemical bond. 3 4 are 12 marks. Okay, SF6 octahedral geometry. I'll start with BeCl2 only. Whatever we did, for all the molecules, we'll apply our method. Beryllium. Beryllium has how many unpaired electrons, students? Not how many unpaired electrons. How many valence electrons? Beryllium has two valence electrons. The two valence electrons you take like this, two dots or stars, your wish. So here, these are the electrons of beryllium. Each chlorine can form one bond with one electron. Yes or no? One chlorine will form one bond with one electron of beryllium. This chlorine also same. So total how many? This is sigma bond. This is sigma bond. Total how many sigma bonds are there? Two sigma bonds are there. No lone pair. So total number is two. Two means which hybridization? sp hybridization. Total number of sigma and lone pairs. BCl3 I did. Boron belongs to 13th group. It has 3 valence electrons. Otherwise, write electronic configuration. You'll come to know. 3 chlorines will form bonds with 3 electrons of boron. How many sigma bonds, students? 1, 2, 3. What is the hybridization? Total number of sigma bonds, how many? 3 sigma bonds. Any lone pair? No. 0 lone pair. So total number is 3. Which hybridization? sp2. I gave in the beginning all I gave. Number of sigma bonds plus lone pairs gives hybridization. CH4 also we did. Carbon has 4 unpaired electrons. 4 unpaired electrons you take up. Not 4 unpaired, 4 valence electrons. 4 you take. Each hydrogen can form one bond with one electron. Total, how many sigma bonds, students? 4 sigma bonds. If the number of sigma bonds 4, what is the hybridization? sp3. So far, what all we did within 3-4 minutes only we could do. PCl5 also I did. Phosphorus has 5 valence electrons. Write 5 valence electrons. 1, 2, 3, 4, 5. 5 electrons of phosphorus forming bond with the 5 chlorines. How many sigma bonds? 5 sigma bonds. So what is the hybridization? sp3d. sp3d. Next. SF6 also I did. Sulfur has 6 valence electrons since it belongs to 16th group. 1, 2, 3, 4, 5, 6. Total how many sigma bonds, students? 6 sigma bonds. What is the hybridization? sp3d2. Only so much. Sorry, NH3 is bit different. No, that also you do. You may get out. That also I will do. You ask. Got it, students? Take number of valence electrons. And whatever the bonded atoms are there, no? Easy in seconds you can do it. No need to take minutes also. NH3 we will do. Students understood?
Yes, sir.
Yes.
Now NH3 we will do. Whatever the examples I gave, everything I'll explain next class. For every molecule, I will apply this. There are XCF4, XCOF4, I3 minus, so many things but only one example I took for formal, theoretical. By using this technique, I explain all the molecules. NH3. Here, nitrogen has 5 valence electrons. Take 5 valence electron. 3 hydrogens can form bonds with 3 electrons of nitrogen. These 2 electrons are free. This is called lone pair. Pair of electrons are there, but they are not involving bond pair alone. Lone pair. Lone pair. So while considering hybridization, what did I say, students? Number of sigma bonds plus lone pairs, if any lone pair is there. 3 bonds are there, no? 3 sigma bonds plus 1 lone pair. This pair, lone pair I told, pair of electrons you have to take like 1 bond. Total how much? 4. What is the hybridization? sp3. Same thing I told.
3.
Yes, sp3 hybridization. In this method, you can come to know hybridization and number of lone pairs also. Number of lone pairs also. Okay, students. In next class, I'll do remaining examples afterwards. Vesper theory and molecular orbital theory. Within 2 classes, the chapter is going to finish. Everything will be covered.